nice. I never, we don't get to see people from Albany very often, so it's nice seeing people in
Well, it's
person
great to
instead
get
of
to
on screen.
meet everybody.
Yeah, for sure.
We've been over at the harbor management meeting, and this is my backup notebook.
Wow.
So,
Yeah, that meeting, we went over for the
Hey,
poster
can you
session.
check that screen for me?
Yeah, once my computer fires up.
Please.
Yeah, once I'm logged on. Yeah, we went over for the poster session the one night. It seemed nice.
oh yeah,
Nice about it.
lots of really good information.
Yeah, I'm sure. Nick, it just says you're
It's
on,
good?
well, it just says.
Yeah, that's what I have.
Okay.
Oh, right now.
Okay.
Man, I'm so sad about people wanting things money to money.
I'm so sad.
Barry is doing nothing.
He said, like, what's wrong with
She was in
him?
the hospital over Mother's Day for 4 days. Come back. Didn't do anything.
Does he even talk? Do they speak?
Yeah. He just had knee surgery for the second time. He said he was in all this pain. She was telling him. I had to hire her. I got a friend of mine to take care of her, so she pays her. But I had to find somebody to spend days with Bonnie to take her all over appointments, because she can't really drive anymore. Craig's, I told you you should have home a long time ago. She's not really leaving home. Her house is all flat. It's no range. She can live in her house if you want. She can do just what she wants.
Right.
She's comfortable.
Yeah, he has no, like,
She's thrown around home.
yeah, he has no empathy for her at all. That's sad. Especially, I mean, he has all the money in the world, dude. He can do anything he wanted for her if he wanted to.
You guys are always having the most interesting conversations. Who are you talking about now? Even though I don't know.
Bonnie's
My best
son.
friend, he goes for a railway.
Oh, this is not the one.
I mean, as soon as they got on the e-bike, I went up there like,
Do you have an e-bike? Do you have an e-bike?
I just got it. It's my new proudest possession. I call it my States house.
Oh,
Yes.
nice.
My friend Brandon has one. He loves it. He keeps trying to talk me into getting one.
They go from $200 to $50,000. So I researched the shit out of it. It goes 20 miles. So I think my car was 23 miles. Not quite up to that.
Yeah.
But it's the one that folds. So I can throw it in the car. Because nobody ever wanted to take my bicycle. So when I was kids, that's all we did. Ride bicycles. So I don't know what happened the first time. I was smiling from my ear to ear
send me the link to it, because I might get one.
It's so worth it.
Everyone keeps telling me about them.
Juliet again, so we get used to the neighborhood with the chips.
Do you charge it?
Charge it, take 1 hour.
Is it just like a regular,
Regular charger.
so you could take it with you if you wanted to go to the city and stuff?
The battery comes in and out. Yeah. Here, look at this. I looked it up. It's called P4. I think it was on Prime days. And I bet Black Friday will be cheap too.
Mm.
I made everybody take a test bed on it. You know, like the 2 batteries, like, oh my god.
I know everyone says how fun they are. I might literally get one. I need,
So
like,
you
I need to
could
do
bike
something.
too, right?
Yeah.
Yeah, you need to go through your partner. You look gone all the time.
Just me riding around Bell Vernon on my e-bike.
Is there like a, is there turntables and stuff on it?
No, it doesn't have church. At lunch, I go like 11:30 at lunch. See in the middle, it holds. It comes in.
Yeah.
It comes in Tiffany blue,
Tiffany blue.
gunmetal gray. It comes in bright orange and black.
Do you have a link to it?
Okay, I'll send it to you.
Yeah, send it to me.
But it folds, and the seat and the handles go up and down. And it's got tires, so it's like a street bike.
Yeah.
But it's got a bell and it's got a speedometer. And the weirdest thing is the left hand is the wrong place because you can break your motion.
Yeah.
So it's over there.
That's kind of different. Although on my jet ski though, it's on the left hand side, so I'm kind of used to
Oh,
it.
so it's probably like a
Yeah.
European thing or something.
Yeah.
Yeah, I'll send it to you.
Yeah, I think I might get one because like honestly, I need like something to do.
I would love if
You
you,
drive it up to your parents, like it's
I would
that.
love if you came into work on
Yeah.
that.
Or
To
you're
work.
on a major highway.
Yeah. Ding ding.
Well, you know one of those, he says, I drive down the road.
Yeah.
I don't work there, but I drive down there.
Yeah.
Get lunch and come back home.
Yeah. Well, I mean, in my little town, like
Yeah,
where
you
we
have the
live, yeah,
sidewalks.
we can go. I mean, yeah, there's sidewalks everywhere.
And you can take it to the park. Now it's 57 pounds, so it's hard to lift for me. So it's like probably really hard for you. But I just love that whole thing. I can't wait to get on it.
Well, we have a trail, Cedar Creek Park Trail, and it's like it goes from our house to Washington D.C. You can ride it all the way to D.C. Which obviously wouldn't do. It's hundreds of miles, but it's just on that trail. My friend
Get
Brandon, he's
halfway
like, you
again.
have to he's like, dude, it's so cool to be on that trail. Like you can go forever. And then he's like, then half the time you're like getting exercise at the same time, you know, like so. Yeah, I'm gonna.
I'm Paige.
Um,
Oh, hey, nice to meet you, Angela.
I like that because I'm always hot.
Yeah, I'm excited that we
well, yeah.
You don't realize
could
you
be
moved out
in
of
the same place at the same time.
I don't know. I might get one.
In the past.
You're the second person now that's been ranting and raving about them. So. $700 is not. It's not nothing in the big scheme of things.
It works so well. Yeah, I was like, no, I get to go see my Mickey Leland speak. So exciting. Whenever I saw like the location, I was like, where's the rock? So I hope it's okay to meet you.
So you and your kind of look alike, right?
Yeah.
Because when we turned
Yeah, it was
the
good. And he was
bio, my notes, I think that they used their mentor's picture for the.
I was gonna say, are you guys, have you reconnected? You rekindled your relationship?
Yeah, whenever first got to see her in person, I was like,
Yeah.
That's funny.
I mean, there's no point of having bad blood. You have to work together no matter what, right? So
Yeah, well, you two together.
you don't have to be around each other all the time anymore. So. Wild, yeah.
But you guys have had a good experience.
oh yeah.
Oh god.
Oh yeah.
Is this your second?
Yeah.
doing it?
Second year doing it. I was a research advisor 2 years ago. But Brian Strawstar, who was the mentor, he was like, just, you're basically, like, I'll be the mentor, but you can be the mentor.
Yeah.
And it ended up, because I was the subject matter expert on the work with the
takes a while to make some changes sometimes, so we'll do what we can.
Lots of moving parts.
Yes. Or you have to wait.
We get it now, get it in now, it'll be implemented in like 2 years.
Right, exactly.
At least it will get implemented.
She's still in the 12s, but, so the people that have the 112 seats, so they just always used to like give them to her, or like she'd buy one of them, and then she texted them and told them that they could sell them online. She's like, yeah, I probably shouldn't have done that, because now we're selling them online. She's like,
Yeah,
I mean, I
of
can
course.
always buy them off of them, but yeah, so she has like the one,
I was able to.
10, and then 5 that we want her spring. They're all hot seats, but we might be able to find the one, but it's still nice. She's 2 club, and I'm wondering if she's gonna put her boyfriend's son, his cousin in the ring.
I mean, it's been working out so far. I think that
That's my comment. like, I can't do it.
But Steven and Zach talk to each other, so like what we could do is Steven probably have to talk to Zach to like figure out what you want to do, and then I'm sure Steven will do that. I think he's but No, he was specifically for the porta potties. Yeah, you don't want to write there? I went to So I don't know if it's possible for me to like even do it during it's quick. I have the flash set. I just don't have access. Like the I don't know if there's a way to get in through like admin because we don't have the passwords to our meetings. So I can't like do it regular. I told my manager, I don't know, maybe once just go in and do everything. I just need to get into the computer. Like it won't even load me because it'll say like doesn't recognize smartphone. And both of my users are and I didn't think I was gonna lose access. So I was like, well, I'll just do it like the last day so that I have all my stuff. That's what I do. Should I try to look at it or can I just leave it here and then or if there's like I don't know if we have like a password to it because I was never given a password. So I don't know how to figure out. Like, can I do a regular login if my computer doesn't go on with that sort of I can tell you?
You can try that. I'm not sure. I'm not really like that. You should be able to. I'll reach out to you.
Okay. Yeah, sorry about that. It's better if we can access my stuff so that I have my data. If not, they just don't have that to use. But if we can, it's okay. Most of it is it's just like a lot of lost stuff.
You weren't supposed to. So that's great.
Yeah. I turned it off, turned it on, tried it a few times, and it just said can't connect to smartphone. Right.
Yeah, before you ask them first, and then see, because sometimes they're like, sometimes they have to take your well and like, you put crap.
No, we never. Yeah. I'll come back after this. Sorry.
Who won? I don't know. We lost. Oh, no, I think Pirates lost.
No, we lost.
They always lose. We could have looked at well, for the UK.
Good morning, everyone. So we'll get started with our first set of presentations. I'd like to welcome now Kendra Beersley.
Good morning, everybody. My name is Kendra Beardsley, and this summer I was under the mentorship of Abigail Martin, working to develop an ontology for geologic data. Just a brief disclaimer before we start. So a little bit about me. I recently graduated from the University of Idaho in May of 2024 with my bachelor's in geology. After MLEF, I would like to take a year to work in the professional industry and then eventually go to get my master's and potentially a PhD. And just as a fun fact, my favorite mineral is fluorite. So to start, what is an ontology? An ontology is a hierarchical system of structuring information in a way that both programmers and programs can understand. So it works similarly to a search engine, where it is capable of querying data in things like servers and databases, but it differs from other search engines in that it is able to understand and infer relationships between different objects and different things. So it creates a shareable context of information. So how does that look in practice? Well, the first part of an ontology is that hierarchical system, which is similar to a taxonomy. So, for example, if a library wanted to create an ontology of all of the media they have in their catalog, they could create an ontology with the domain library. The domain is the overarching umbrella under which all of your information should fall under. So everything should be able to link back to the domain. It's the highest level of ontology, and underneath it you have classes. And classes are subsets of knowledge or genres of knowledge within that domain. So in this library example, you could have books, you could have articles and magazines, and those would all be different classes. So they're the middle level of the ontology, and for the lowest level of the ontology, you have individuals. And individuals are instances of a class. So in this case, The Hobbit would be an instance of a book. So with that, that's the hierarchy part, and you can get to the relationships part. And the relationships are described using things called slots or properties. And the first kind of property that you have is an object property. And those link individuals to other individuals. So in this case, The Hobbit could have the object property prequel, which would link it to the other individual in the class book, The Lord of the Rings. And the last kind of property that you have is data properties. Those link individuals to values, also called literals. So The Hobbit could have the data property number of chapters with a value of 19, because it has 19 chapters, or it could have the data property year released with a value of 1937. So what does that look like when you put it all together? Well, this is a commonly used program for building ontologies called Protégé. It was developed by the Stanford Biomedical Sciences, and it has these relationships structured in such a way that it creates a descending order. And so in our Hobbit example, we would have the library as that domain over there, but you can see it also has the option for subclasses, and subclasses could just be more specific subsets of knowledge. So book could have the subclasses romance, fantasy, nonfiction. The Hobbit would fall under fantasy. And then I didn't mention it on the other side because it's not as common, but annotation properties allow you to append different subsets of knowledge to an individual. So if you have a string of information, like a paragraph that doesn't fit in the most other data types, you could attach it using the annotation property. So for this project, we wanted to develop an ontology for some of the data that is hosted on the Energy Data Exchange, which is the FECM and the Department of Energy's data hosting server. We wanted to create one that specifically focused on critical minerals. So we focused on finding data sets that had consistent layouts, good quality metadata, and then spatial and temporal information, because my ontology had the domain geologic timescale, because it is a very, it's a relative standard of sharing information across multiple different countries, and it remains relatively standard as you move through time. So using that Protégé 5, I worked to develop that ontology and build the framework. Once you have the skeleton of the ontology, you can work on importing individuals, and that's where things get tricky, because most of the time you have to import individuals by hand. So we turn towards finding ways of importing large amounts of individuals at once. And of course, find a way to help visualize that, because most of the relationships are best seen when you visualize it in a web like you saw earlier. So again, the process was to identify a candidate data set. once you had that data set, we used two specific ones, one ending in the serial number 53 and one using the serial number 55. They were the most extensive, they had the most extensive metadata that we could find. And once you go through, because ontologies are a method of standardizing information, you have to go through and make sure all of the data is talking about the same thing. So if you have a country that's US, United States, and USA, those are all talking about the same thing, but the ontology will only look at those as different things. So you need to make sure that all of those are equal, so we set them all equal to United States of America. And you have to make sure that the values are all the same. So if you have a length of core, if someone is measuring their core in inches and someone else is measuring it in centimeters, those aren't consistent either. After that, you have the ability to use a plugin for Protégé called Selfie. And Selfie runs on Mapping Master Syntax, which is a syntax specifically dedicated towards converting Excel sheets into an ontology readable format. So after that, you can add cardinality, which describes specific relationships. So you have only, which would, for example, be, you can only have The Hobbit in the category of book, because it's not a magazine, it's not an article. So this was our result. This is a visualization of the experimental core ontology that I built in the web application WebVowel. And here, the classes are represented in blue circles. The object properties are represented in little green boxes, and data properties are represented in the orange boxes. The domain is in the center. Let me see if that'll work. Okay, well, you can see it in the middle of the ontology. It has a bunch of green circles and a bunch of orange boxes around it. And because the WebVowel does not have an application for spatial data, we used ArcGIS Pro to go in and add the spatial information. Not all of the data had spatial information, but the ones that did, we made sure to plot here in latitude and longitude, because a lot of them were also using different coordinate systems. So we developed a ontology that was machine readable and able to be exported, improved upon, and merged with other ontologies. So you can create one massive ontology for the entirety of EDX eventually. It's able to show how all of the objects in EDX are related in a way that is able to be understood by machines, which is very important for things like machine learning. And if we want to go in and start building data scrapers or things like that to help improve our knowledge and the accessibility of that information. So the future of the ontology could look something like this. This is a very old plugin for Protégé called Walrus. It works to visualize ontologies in 3D in a fisheye view. This is important because it shows it in 3D, in three-dimensional space, which we would really like to use in the future to show how data is related through 3D space. It wouldn't be entirely accurate because the Earth is not a perfect sphere, but we could show the relative locations of where each sample was taken alongside the ontological structure of its relationship to other data within the visualization. And so with that, I'd like to say thank you to Mickey Leland and ORISE for this opportunity. A big thank you to my mentor, Abigail Martin, who's here today, and to my fellows. Thank you. And I can take any questions.
Hi, great presentation. You touched upon it a little bit, but I was just wondering if you can talk about like the biggest advantage to seeing data in 3D space.
Yeah, so for us, specifically, it's really specific to geology in this case, because a lot of geology and this information that's hosted on EDX relies on samples that were taken in the field. Being able to see where those samples were taken in relative space alongside the ontology, it could help show relationships that we might not be able to understand otherwise. So things like lateral continuity of geological units across space, combined with maybe other properties that we wouldn't really consider thinking about if we didn't see that represented visually.
Thank you.
Yeah, thank you for the question.
I'm coming from like a graph theory perspective. I see that a lot of what ontologies appear to be are in a tree structure, but I'm curious about if there's ever like redundancies in the system where files are stored in separate or in multiple places at the same time.
So that's actually one of the big advantages of a good ontology is a good ontology won't have redundancies, and because it's able to relate information in multiple different ways, it's not limited in the kinds of relationships that the data can have. You could have it so that this one thing over here that normally wouldn't be related to this other thing over here is related without having to put this thing over with this thing, if that helps. Yeah.
Could you speak for a second on how that's done procedurally?
Yeah, so here, I'll go back. So for the object properties, you're able to set cardinality, which defines how or what kinds of data can go in between the relationships. So cardinality is one way of improving like accuracy and relationships and removing that redundancy. And then you have the other level where the user can go in, and that's one of the other benefits is that a user can set it. So most of them have the structure like has blank, but you can also have, for example, is part of blank or is related to blank, stuff like that. So you can get really, really specific with the relationships that you want to convey. And the ontology with cardinality and those properties, it can understand like, okay, this thing is related, but it's not, it doesn't need to be put in the ontology again. I don't know if that helps. I hope so. Okay, great. Yeah. All right. Thank you. Our next presenter is going to be Mia Scholdbach.
Hello, everyone. My name is Mia Scholdbach. My mentor is Paige Morkner, and this summer my project was testing the geospatial and information anonymization tool, also known as Giza. Disclaimer, I go to Smith College. I'm majoring in statistical and data sciences. I'm going to skip a bit of this just because we've got a lot to get through. One thing that we've seen throughout the past week of MLEF presentations and even like the FECM presentations down at the convention center, if you've had the chance to attend those, is that the Department of Energy produces a lot of data. And sometimes that DOE data can contain sensitive information. Now, as scientists, we want to be able to share our research with the public and publish, but sometimes in order to protect, say, industry partners that want people to sign NDAs, that data has to be anonymized before it can be shared with people. Anonymization itself is a pretty complicated topic, but for this presentation, what you need to know is that it's basically removing some parts and some information from a data set but still retaining that usefulness of that data set for analysis. Now, that's the reason why Giza was developed, in order to help scientists at the DOE to anonymize data. Because before it had been a pretty time-costly process. So as stated before, Giza stands for the Geospatial and Information Anonymization, Geospatial Information Substitution and Anonymization Tool. And this tool contains a lot of different methods of anonymization. It can anonymize text files and the contents of text files, but what we'll be focusing on today is its geospatial anonymization features. Giza contains 3 different methods of geospatial anonymization. There is the cluster anonymization, which is basically, instead of visualizing every single individual point in the data set, it visualizes how many points are in a certain larger geographic region. And then we have LSH anonymization, which in this case means locality-sensitive hashing, which is repositioning points based on their relationship to each other. But what we'll mainly be focusing on today is, this is the Giza tool layout, sorry. The buffer anonymization. So this buffer anonymization, as you can see here, you have this circle here. The point here is repositioned to somewhere inside this outer circle, but not inside this inner circle, so it's sort of a donut shape. Now, Giza also has these constraint layers to where this buffer layer can be restricted based on the value of that polygon layer. So instead of just anywhere inside this donut, it's just this specific area. And that depends on whether Giza is, the point that Giza is plotting is inside that polygon, where it will be replotted inside the polygon, or outside the polygon, where it will be replotted outside the polygon. Now, Giza had not been bug tested extensively, so that was what my job was this summer. The project at first consisted a lot of running Giza various times, and then looking at those data sets, including in ArcGIS. Here you can see there's a model builder in ArcGIS model builder that kind of shows one of the basic processes of what I was trying to do. And that involved sometimes visually recreating these sort of donut-shaped buffer layers, and also looking at the input data sets, the output data sets, and the buffer constraint layers individually, and seeing if there was anything unusual. So for results, one of the main things I'm pretty proud of is this discovery that there were some errors in the way Giza was reprojecting points. An example of this is shown in this image. So you can see here, this is the census tracts layer. So this blue point at the top, which is the individual, like our input point, should be replotted inside the census tract it's in, which is this highlighted area. But as you can see, this orange point is where it was replotted, which is obviously not in that census tract. So we have an issue here. And it was discovered that the reason that this is happening is because when Giza was reloading certain buffer constraint layers, it was doing it incorrectly, so that it was placing points inside the buffer layers, but not the actual buffer layers. There are also some edits made to how Giza exports output data sets so that they are easier to work with in ArcGIS. And also there were 7 new iterations of Giza produced throughout the summer to address issues. Moving forward with Giza, one thing that I would hope to be standardized is how Giza deals with water and water bodies. Giza has 3 different buffer constraint layers that represent water bodies. You have the NHD flow lines up here, which is supposed to represent stuff like rivers. You have the world seas buffer layer, which is supposed to represent world seas boundaries. And you have the NHD water bodies layer, which is supposed to represent water bodies in the US. But the NHD flow lines and NHD water bodies layers come from a different data set than the world seas buffer layer, so that they are not standardized what areas are counted as a US water body and what areas are counted as a sea. So as you can see here in this image of the Chesapeake Bay, most of this is counted as a water body, but then you have these little areas up here which are not. And that NHD flow lines area is not going to make up for that because it's just making sure the points aren't plotted on that line. And even if you look in here really closely, there's still some like blue areas that are not covered by the combination of all 3 of these constraint layers. So that's one thing that I hope would be looked into in a future version, potentially maybe swapping some of these out for a different buffer constraint layer data set. I'd also like to look more into the code for cluster anonymization because some of the points didn't seem to be maintained in the final visualization, because if you can see the number of points that are in a certain layer, they should all add up to the total number of points in your input data set. But I was seeing some instances in which this wasn't the case. We didn't get a chance to look into this immediately just because this particular part of Giza was coded by a third-party contractor, so that complicated the process of getting access to that code. I would now like to move on to acknowledgements before taking some questions. I'd like to thank my mentor, Paige Morkner, my research supervisor, Patrick Wingo. Sorry, there's a lot of acronyms that I'm going to have to read here, so I want to make sure to get everyone in. Everyone at NETL, everyone at FECM, everyone at ORISE, and of course, everyone in the MLEF team.
Very cool project, thank you. I'm wondering how well it holds up against geologists who are experts in the region. So I've had to do this in the past. I've had to take a survey that the serial numbers have been filed off, and I've had to figure out where in the world this is. So I'm wondering how well it works against experts.
I think that's something that might need more testing. A lot of the things is we want the points to be replotted in a similar enough area so that, like, say they're in the same geologic layer, or something like that. But we don't want them so far, so close that you can easily identify where they were. My background's not in geology, so that's kind of a hard thing for me to test. But that could be an avenue for testing in the future.
Thank you.
I'm curious about if the inner area of like the donut caused any issues where it was like too large and excluded the entire region.
So that's something I would have liked to get tested. One of the things that I was not expecting to be so difficult was I tried to, in ArcGIS, recreate, oh, sorry, we're going a bit too far back. I tried to basically recreate these buffer layers in ArcGIS, but at least with the tools I had access to, it's kind of hard to create a ring-shaped buffer without either like one of my ideas was, okay, well there's like a multi-ring buffer. So what if I can delete one of the rings? And to my knowledge, there's no way to do that without iterating through every single point. And that is something that's possible to do with Model Builder, but it also, you are creating a bunch of like individual separate layers in ArcGIS in the process. So it's kind of hard to do because of like the amount of files that would be created. There was something I discovered towards the end of this process that I think might have been an easier way to do this. But by that point, I was like, I'm gonna move on to some other stuff because recreating images of every single buffer layer for every single data set I've tested is going to be kind of difficult. And also the default minimum buffer that I was using, that Giza sets, is 1 meter. So if you are looking at a map of the US and you see you have these buffers that have a radius of, I believe it's 100,000 meters, seeing that little 1 meter buffer inside is pretty much impossible. So at that point, I was like, while I can actually visualize to test these, I think ignoring the inner buffer layers for now is probably the best process, just because I was using that as a way to use ArcGIS's select by area tool to see which points are inside this buffer and which points are outside, and if that is what I would expect from the input data set. Sorry, I realize I'm kind of going on a tangent, and this would also be a lot easier to show you if I had visualizations of, and like all my files, but yeah.
Hi, really good presentation, by the way. I'm genuinely curious, as someone who's worked with ArcGIS, I know water bodies can be difficult, like computationally intensive, because of how amorphous they are. Does Giza simplify polygons around water bodies, and does that create any issues? And if so, how does it handle it?
Oh boy, you have just ended up on something that puzzled me for weeks. So this NHD water bodies layer is incredibly computationally taxing. So much so, it's more than any other layer. This is the only layer I had issues running on my computer. Because it requires you to have, it took us a while to figure out why this wasn't working, but at least on my computer, if you're running it, it requires you have like 6 gigabytes of RAM, and not just like 6 gigabytes of RAM, but like 6 gigabytes of RAM that are like completely free and not like split up in any way. So in order to run this and test this, I had to remotely access a computer in Albany, and even then it still takes a while. Like, for example, some of the larger tests on this, I had to set up the computer to run overnight, because if I was doing just this NHD water bodies layer with like one of our larger data sets, which had like over 1,000 points, that I'm pretty sure it took over 8 hours, if I'm remembering correctly. It could have taken like near to 10. So that's one of the things. I also think that if we connected some of these smaller polygons around here, like as you can see, like that up there, I think could be considered part of the Chesapeake Bay. But since it's a completely different polygon since this area isn't connected. And so I think connecting some of these areas might actually help with the process because you have fewer polygons. I also think possibly simplifying the NHG water bodies layer might be good, or instead, like, it's kind of a trade-off because if you are trying to put a lot of points in a smaller area, one of the data sets that I was later used was a series of points concentrated in northern Illinois. And if you simplify these points and simplify these water bodies, chances are a good amount of your points are going to be ending up in one of the Great Lakes. So it's kind of hard because sometimes it's like, do you want to give up some of that like accuracy and potentially have points going in the water, or do you want to have it so that it's actually usable by the average person? And I think that's something that has to be looked into going forward. Sorry, rambling again. And next up is Dash Kamriani Beard.
All right. Hello, everyone. My name is Dash Kamriani Beard. This summer I worked at Lawrence Berkeley National Lab with Dr. Bhavna Arora and Dr. Dipankar Dwivedi. And I performed a sensitivity analysis of subsurface carbon mineralization resources in Hawaiian basalt. Here we go. So yeah, a little bit about me. I'm a senior at the University of Illinois, Urbana-Champaign. I'm getting a bachelor's degree in computer engineering with a minor in astrophysics. This fall, I hope to continue research with a telescope in Chile. And I'm from the Bay Area. I love rock climbing and learning about things in space. So a bit of an intro. As we know, human CO2 emissions since the Industrial Revolution have become a major issue for our existence. Climate change has become more and more of a threat, and the main solutions focus on reducing CO2 emissions, like switching to electric cars or sustainable energy. However, studies have shown that reducing the emissions that we are producing by the most we feasibly could, which is around 50%, is not enough to reverse the effects of climate change. So one potential solution is carbon capture and storage, which is basically taking carbon out of the atmosphere and putting it somewhere else. There's a lot of research in how to take the CO2 out of the atmosphere. So what my project is focusing on is where do we put the CO2 once we take it out of the atmosphere. So as for some potential candidates for carbon capture and storage, so sedimentary basins have been extensively studied for storing carbon. This is because they have high porosity, so there's a lot of space to put the CO2 into. However, when you put CO2 into a sedimentary basin, it is only trapped physically. So it's basically just being put down there in a container. This means it's difficult to guarantee its storage long term. Another avenue is putting CO2 into basalt. There are advantages to basalt in that it's very large. There's a lot of basalt around the world, and it has a large storage capacity. So actually, almost all of the world's CO2 in the atmosphere can be stored inside of basalt, just physically. But the real advantage is the fact that basalt can undergo a process called mineralization. Mineralization is when a gas or some other material is exposed to a type of rock and reacts with the rock. And generally the gas will bond with the rock and form a new rock. So in this case with basalt, CO2 reacts with basalt and forms carbonates. So furthermore, basalts have high porosity and permeability, which is very good for mineralization. So where can we find basalt to store CO2? There have been two projects, pilot projects. One is done by PNNL in Wallula, Washington. This stored 1,000 tons of CO2. And then another one is the CarbFix project in Iceland, which has stored quite a bit more, 100,000 tons of CO2 as of today. But both of these projects have run into various issues and have not really operated on as large of a scale as we need. There are 950 gigatons of CO2 in the atmosphere, so these amounts are still very small. So one very promising candidate for mineralization is a type of basalt called pillow basalt. This is formed when lava erupts from below the ocean, when volcanic islands are being formed, and cools really quickly. So it forms this formation called the pillow basalt, which is very round, and it has high porosity and permeability, which means the CO2 can flow into it very easily. This type of basalt has been extensively studied in lab, and very large basins exist around the world, which means it's very promising for mineralization. These basalts are actually what are in the CarbFix project, but a big issue with that project is that it's at the site of injection is located very far inland, which causes the temperature underground to be very high. This makes it so that you have to pre-dissolve the CO2 in water before you inject it. However, CO2 is only 4% soluble in water, so this is not very efficient. So this brings me to my project, studying Hawaiian basalt. So the focus of this project, is inspired by work done in Hawaii from the late 90s to early 2000s called the Hawaiian Scientific Drilling Project, or HSDP. This project drilled 2 wells with the goal of understanding the stratigraphy, or the geology underneath volcanic islands. The specific well we're analyzing is 3 kilometers deep, and yeah, we think it's very has a lot of potential for carbon capture and storage. This is based on core samples and a characterization of the site, and based on that characterization, we've realized that nearly 100 megatons can be stored in this single basin alone, with potential for a lot more throughout the Hawaiian Islands and the Big Island itself. So yeah, some advantages of this site are that you can inject pure CO2. Because the basin is very close to the ocean, it gets cooled by the water, and that makes it so that we can inject pure CO2. We don't have to worry about it coming back out. We also, there are a lot of ways that CO2 can be trapped down there. First and foremost is mineralization, but also because of the low temperature, CO2 will have a high density, which means it will tend to flow down the basin and not come back up. Furthermore, another trapping mechanism is called CO2 hydrate, which is when the CO2 flows near the ocean, in the basin near the ocean. This thing called CO2 hydrate will form, which is basically the CO2 getting trapped by smaller molecules of water. So we don't have to worry about the CO2 leaking into the ocean and causing more problems. So this is where my work comes in. So from the site characterization, we only have permeability and temperature data down to 2 kilometers, but we're planning to inject CO2 at around 3 kilometers where the pillow basalt is. So some big questions are, do these basalt formations allow for significant CO2 sequestration with the different possible temperature and permeability configurations that might exist down there? And then also, how do these parameters affect CO2 storage? So I started off by modeling our system in a software developed by the lab called ToughReact. It's developed by the lab, and it's capable of simultaneously simulating the flow of CO2 underground and the reactions it experiences along the way. That process as a whole is called reactive transport. So I started off by making a model of 3,500 discrete blocks, which model an area 3 kilometers wide by 5 kilometers deep. Or other way around, 5 kilometers wide by 3 kilometers deep. Then I split that into 3 layers of homogeneous rock, so subaerial lava, hyaloclastite, and pillow basalt, which is what we're looking at. This is based on the HSDP data. And to simplify the way CO2 is being trapped, I made the entire system isothermal, and I made the dip angle of each layer 0. So these are some of the minerals that or primary species and minerals that I simulated. Basically, the ones on the left, every grid block has a certain concentration of the things on the left, and the minerals on the right can be formed from those species. So as reactive transport happens, we can calculate the amount of carbonates that are formed, the carbonate type minerals from that list, and figure out how much CO2 has actually been mineralized. So to conduct my sensitivity analysis, I used a Jupyter notebook to generate 25 simulations with varied parameters. This is based on a site characterization we performed recently, which you can see on the right, based on salinity data. And from that, we know that the temperature range of the well is about 32 to 100 degrees Celsius. And the permeability is approximately 10 times 10 to the negative 12 to 10 times 10 to the negative 15 Darcy. And so here are my results. So we can tell on the left that there's a pretty clear correlation with temperature and mineralization content. As temperature increases, mineralization also increases. On the right is my permeability graph. And as you can see, it's a little bit confusing at first glance. So we can see that permeability increased level of mineralization when you increase permeability, mineralization increased, and when you decrease permeability, mineralization increased. However, there are different reasons why this is happening. In the high permeability situation, we can reason that the CO2 flowed more at the beginning, and then started mineralizing later after it had expanded into the basin. This is advantageous. This is the behavior that we want, and I confirmed this later by looking at flow data. This is my pipeline that I developed for generating simulations. This was a big part of this project. Basically, it sped up the process of generating simulations by a lot. ToughReact is a very complex software for any of you who haven't worked with it. It has hundreds of pages of documentation. So this speeds up the process of making new simulations exponentially. As for my conclusions, so our sensitivity analysis showed that temperature and permeability both have effects on CO2 sequestration. This results in a greater understanding of our system and allows us to predict what will happen in the field based on certain conditions that we can observe. So some future directions for this work are applying machine learning to improve the optimization of mineralization. That was one of my goals. I didn't have time to do it. But basically to tell a model what we want as an output, and then it will vary the inputs for us to optimize that. Furthermore, next we're going to model and analyze newer sites for this type of research, such as the next project is a drilling project in Oahu, which will do similar type of analysis, but other volcanic islands such as Japan or Iceland or the Aleutian Islands in Alaska all are future targets of this mineralization. Altogether, these places have the potential to sequester gigatons of CO2 from our atmosphere and make a huge impact on our planet. So I'd like to acknowledge my mentors, Dr. Bhavna Arora and Dr. Dipankar Dwivedi, Eric Sonnenthal, who's the author of ToughReact and who helped me a lot with debugging, the Hawaiian sequestration team as a whole at LBL and the University of Hawaii, ESA at LBL, and the MLAF and ORISE teams. These are my references. Any questions?
Hi, first of all, great job. I was wondering if you made any graphs or phase diagrams or anything that factor in pressure.
I did not. So we were kind of assuming that pressure was pretty much equal, but that was a future direction that I wanted to go in. So the only two parameters I varied were permeability and temperature.
Sorry, one more thing. Did you think about different compositions of basalt?
Yeah, so originally we simulated a different older model of basalt. But recently, there's been work done to characterize more of these kinds of sites, like other drilling experiments. So I actually updated the composition of my model completely, pretty much at the beginning of my project. Yeah, so there was a little bit of a difference, but the trend was relatively the same.
Hi, Dash. Fantastic presentation. And I understand if this question's outside of the purview of what you specifically researched, but what are the sort of plans to get that quantity of CO2 to somewhere as remote as Hawaii?
Yeah, so the big way that we are getting CO2 for sequestration is something called point source capture, which is where you go to where the CO2 is being emitted, like an oil rig or something, and then taking it and putting it there. So we're trying to, a big reason why we want to expand this into other islands like Japan and Indonesia is because they have a bigger need for this. Like they have a lot of factories, they have a lot of production, and so that would be able to offset their emissions significantly. So right now, I'm not really sure where the CO2 is coming from for this project. That'd still be a few years out. But yeah.
Are there, I guess, different challenges with doing something like this in an island like Hawaii where its devulcanization is caused by a hotspot as opposed to, say, islands like Iceland where it's caused by tectonic plates?
Yes. So generally, it's actually better at hotspot islands. That's why a lot of the research is being focused on Hawaii and other volcanic islands or hotspot islands, because the way that they form is in like a cone shape, and that makes it so that it cools the sides of the volcano a lot, which makes that region in the sides very good for mineralization. So yeah.
Thank you.
We are out of time for questions, but I do encourage the students to reach out to the student and ask your questions.
Yeah, so I'd like to introduce Samaya Derrick as the next presenter.
Where's the laser pointer? Okay, that's the laser pointer. There we go. All right. My name is Samaya, and I'm going to be talking to you about orphaned wells. So my project this summer was quantifying methane emissions from orphaned oil and gas wells. I worked out of Pittsburgh under the mentorship of Natalie Peckney. So, a little bit about me. I go to UCLA. I study environmental science. I'm minoring in GIS, and some goals after, just like everyone else, completing my last year of the program, gonna work for a few years, come back, work in the energy sector. Fun fact about me is that I have perfect pitch, and people will not leave me alone about it. So I'm gonna just talk a little bit about methane as a climate driver first. So methane is 28 times more potent than carbon dioxide and has huge heat trapping potential. So a little bit about how methane emissions are quantified. They're done by the U.S. Greenhouse Gas Emissions Sources and Sinks by the EPA. So as of 2022, we had a few different emission categories. Gas production, okay, laser pointer, gas production, oil production, processing, transmission and storage, distribution, post-meter, but as of 2018, a fresh, new methane emission category dropped, which is abandoned wells, coming in at 4% of emissions. And I know 4% doesn't sound like a lot, but 4% is still 8.8 million metric tons of CO2 equivalent, so don't forget about us. So what are abandoned wells? Abandoned wells and orphaned wells, I'm going to be talking about them simultaneously, so they're the same thing. Abandoned wells are wells that no longer have a responsible owner and are property of the state. They are usually leaking, and as of 2018, they are on our radar. So the government is flowing a lot of money into 3 phases of orphan wells: discovery, finding the orphan wells, quantifying them, and then plugging them. And the thing is, orphan wells don't all have the same emission rates. Some are very small emitters and some are very large emitters. So this project really was to just try to find a way to find a well's true emission rate the fastest way possible. So a little bit of history about Pennsylvania's oil boom and ramifications. So Pennsylvania had an oil boom from around the 1860s to the early 1900s, and there were thousands of wells drilled throughout the state. The area of study that I did was called Hillman State Park, used to be called 5 Points. It was, there were at least 170 known wells, and then it was strip mined. So this is one of the abandoned industrial structures at Hillman State Park. There were also, other than wells, just a lot of debris, old engine houses, really just abandoned. And Pennsylvania is one of the hot spots in the country for abandoned wells because of this oil boom. So the project's significance and goals. So this summer I wanted to standardize the process for quantifying methane emissions at orphan wells. This project was kind of planned because of last year's intern, what she found. So last year, there's usually this spike in methane emissions when we first start. I'll explain that later. Pretty stable until the second hour where we see this hump. I was like, I don't know why that could be. So this led to concerns on how long we should actually measure an orphan well to get its true emission, because if we're getting to the second hour and it's significantly higher, then that means we need to sample for longer periods of time. So, yeah. The study area, as I mentioned, is Hillman State Park. And for the discovery phase for a lot of these orphan wells, we use drone aeromagnetic surveys, where a drone flies in a grid pattern over a certain area and can take just like the magnetic, pick up the magnetic casings from the well. They have a very distinct thing that pops up. So this is how this map was made, not by me, but from 2014, the last aeromagnetic survey from NETL. So this study took 10 wells throughout Hillman State Park and did 2-hour experiments at each well. So a bit about the field equipment and procedure. I spent a lot of time outside this summer. So the main instrument I used was the Semtech High Flow 2 Fugitive Methane Sampler. I'll be calling it the Semtech. So this measures methane in grams per hour and goes right up against the leak point at the orphan well. Since we wanted to measure also the wind, this Airmar weather station instrument is set up next to the well to measure wind speed and direction. Then there's the remote methane leak detector complete solution, which allows users to kind of point. It is a laser pointer and measures where the methane is coming from so we can pinpoint where to put the Semtech. Then there's the forward-looking infrared or FLIR camera, which allows us to visually confirm that all the methane is being collected. So a little bit more about this camera. On the right, we see high sensitivity mode. You can really see that methane coming out. It looks like smoke. And this is in automatic mode, where we can see kind of wisps, but it's much harder. So I usually utilized high sensitivity mode. So after these tests on the 10 wells, I did a few statistical analyses. The emission range was kind of just to get a ballpark on each of the wells, see how much they were emitting. A histogram showed the distribution throughout the experiment. Median and mean, pretty self-explanatory. And then I did a test where I took random samples throughout the measurement to see if they were statistically significantly different. Then a NOVA test, which was similar to the random test, but took 5-minute increments throughout the entire sample to see if there were statistical changes. And then just a measure of wind versus leak rate to see if wind was a significant factor. So a little bit about the casing significance. Abandoned wells are found in different conditions, whether environmental or historical conditions led them to be like this. Sometimes it's an intact wellhead and with a secure leak point. That means that the methane is leaking right from like the side in this pipe here. Those are the easiest to measure because we can put the Semtech right up to the leak, and when we see it in the camera, there's not really any leakage. This one's a little trickier, wells with an open casing, the type of well Sam talked about yesterday, where it's kind of just like a pipe out of the ground. These ones are harder and is where the wind measurements came into play. Then there was only one type of this well, but it was a doozy, an intact wellhead and a moving leak point where the methane actually leaked through the water and moved throughout the sample, so we couldn't accurately sample it. So I'm going to go through an example of each type of well because they all shared like patterns. So first, an intact wellhead and a secure leak point. So when we measure orphaned wells, there's always this spike at the beginning, this huge spike. But that's only because at the top of the well, methane slowly leaks out like smoke and then is stagnant at the top of the wellhead. So when we start that fugitive methane sampler, it works kind of like a vacuum where it initially sucks all that methane that's at the top of the well. So that's why we get that spike. It's not really significant. But then we see very stable emissions throughout the rest of it, which are statistically identical if we took any random chunk. Then here on the histogram, pretty even. It's not going between that big of a region. And then the wind, it's pretty inconclusive so far. Okay, so a bit more about the random tests. I wrote some code so that I would get 10-minute random samples throughout the period. I just wanted to know if I took a random 10 minutes, are they significantly different enough where we would have to sample for longer? Turns out it's like 0.4 grams per hour difference. It's not really that different. I was very pleased that this was so, like, the averages really averaged out. Okay, open casing, we see a very similar pattern with this spike, but then there is significantly more noise. And remember, that's because it's an open casing, so there's outside environmental factors going on, so it's not as, it's more. And we see very similar, pretty even distribution, and again, inconclusive wind data, but looks pretty good. Now, for the doozy, well 56. So we can see we don't really have a spike. It goes to 0. It kind of evens out. It goes to 0 again. That's because it was bubbling the whole time. It was bubbling, and then it stopped bubbling right about here, right about the 45-minute mark. So for wells with a moving leak rate, I was like, well, we probably have to sample for significantly longer durations because I could not draw conclusions from this. So ultimately, the recommendation was 15 minutes is the magic number if it's a non-moving leak point. The first 5 minutes flushes out the initial methane that's at the top of the well, but then the final 10 minutes, if you average it out, it's statistically the same as if you had sampled for 2 hours longer. So for some conclusions, when 10-minute samples are extracted, the range between samples becomes negligible. 80% of wells held the emission pattern of an initial spike and then stable methane emissions. The 2 wells with open casings exhibited greater amounts of noise and greater changes because of wind. And then abandoned wells with methane emitting from water within the well may require longer durations of data collection. For future work, further statistical analysis should be done for more longer duration intervals to see if there's a minimum duration for which the interval emission rates are not significantly different. Further analysis should be done comparing wind data, including noise reduction, just because it was a lot. And then finally, longer sampling at wells with moving leak points should be conducted to find patterns in emission rates. So I just wanted to thank my mentor, Natalie, thank you, and everyone at NETL, and then everyone who was part of this wonderful program on both sides. All right, questions? Right here, Max.
Hi, Samaya. Great job. At the beginning of the presentation, you talked about the graph from the last interns program and the hump that you saw at like I don't know if you said it was the 1 or 2 hour mark. I was just wondering if you ever figured out what the hump was about, or if you just never saw it again in any of the other data.
Oh, yeah. So last year they didn't measure the wind. So I think it's because of the wind. Because it was I'm pretty sure it was at an open casing well. So it was pretty much the wind.
Thank you.
Yeah.
I'm not sure 100% if you talked about this, but did you factor in the wind into your statistical analysis?
So I did not factor the wind into the statistical analysis. For most of the, for the wells, they were closed casing, so it didn't matter that much. But definitely as part of the future work, the wind needs to be worked in. I just didn't have like the capacity to do noise reduction and then figure out how to factor it in.
We will now take a short break and resume presentations at 10:15.
Oh, cool. Okay. Hi everyone, my name is Sophie Vazadola. This summer I worked at NETL Pittsburgh under Dr. Lauren Burrows, and my project was focused on developing methods for detecting nitrosamine compounds produced from point source capture CO2 emissions. So, oh my god. Wait, what? Oh my god, I'm so sorry. Disclaimer. Okay, like I said, my name is Sophie. I go to the University of Pittsburgh and I'll be a senior this fall. I study chemistry and I'm also doing a sustainability certificate and an honors joint degree. After I graduate, I'll be applying to PhD programs in atmospheric sciences and chemistry. So by now we're all familiar with what a greenhouse gas is, but just for completeness, I'll define it for you. A greenhouse gas is any gas that will trap heat in the atmosphere. And there's many different types. There's CO2, methane, water vapor, and fluorinated gases, and it's normal and actually necessary to have some concentration of these in our atmosphere, but because of human activity, we've seen a dramatic increase in greenhouse gases such as carbon dioxide. You can see in this graph from NOAA over here, you've seen like a dramatic increase over time, and so last year in 2023, we broke yet another record at 419.3 parts per million, which is 50% higher than pre-industrial levels. And a majority of this will come from fossil fuel combustion. And because carbon dioxide is a greenhouse gas, we've also seen a dramatic increase in average global temperature, also referred to as global warming. So point source capture is one technology that can help reduce our emissions of carbon dioxide by removing CO2 from flue gas after fossil fuel combustion. So when you burn fossil fuels, you produce a lot of different gases, including carbon dioxide, and normally this is just emitted right into the atmosphere. The most advanced method right now for point source capture is absorption to amine-based solvents. So carbon dioxide can react with the amine and then stay in that solution instead of being emitted out into the atmosphere. And you can also recover the CO2 later and use that in a variety of industries or just store it long-term underground. And overall, point source capture using amine-based solvents may reduce CO2 emissions by over 90%, so a very large figure. Flue gas is not purely carbon dioxide. It contains a lot of different oxidant compounds such as SOx and NOx and oxygen, and these can react with the amine to degrade it and form a variety of different compounds. And the most concerning that we know of are nitrosamines. So nitrosamines are a class of compounds with an N-nitroso structural motif. So that's seen over here. You have the amine down here, and then the nitroso group up here. And overall, these are broadly probable human carcinogens and mutagens, and they're also linked to other negative health and environmental impacts. And so as we scale up the use of point source capture and move on to pilot studies, it's really important that we're conducting testing at point source capture sites. So that's the long-term goal of this project, to deploy a mobile lab for emissions testing at point source capture sites. And there's kind of two parts of this. There's the real-time emissions testing. They'll focus on air emissions and use instrumentation such as PTR-MS, FTIR, and GC-NCD, which I will not define right now. And then there's also identification of unknown and trace products, which will be done at NETL. So that will be done on condensed gas phase emissions and use instrumentation such as GC-MS and LC-QTOF or LC-MS-MS. And that was what I focused on this summer. So I developed methods for GC-MS and LC-MS-MS analysis, and I also did an nitrosation reaction with piperazine, which is a secondary amine. So just to give a background on the instrumentation that I used, broadly I used chromatography and mass spectrometry. So chromatography is a technique that allows for separation of mixtures based on affinity for mobile and stationary phases. So your stationary phase in column chromatography is a column, and then your mobile phase is a carrier. And GC and LC are named after the state of matter of your carrier. So gas chromatography uses a gas, and liquid chromatography uses a liquid. And the output of this is a chromatogram, which will be response over time, but more importantly, it shows peaks that will correspond to individual compounds. Mass spectrometry is a bit more complicated, but it ionizes the sample and then measures the mass-to-charge ratio of that compound. And this allows for identification of compounds. So if it fragments a lot, you can identify based on the fragmentation, which is very characteristic of that compound. Or if it doesn't fragment all the way, you can identify based on the mass-to-charge ratio. And the output of this is a mass spectra, which will plot abundance versus mass-to-charge ratio and show the fragments. And so when you put these together, you can have peaks from the chromatogram, and then each individual peak will have a mass spectra, so it allows you to identify individual compounds in an otherwise complex mixture. So moving on to the GCMS method that I helped to develop, I mainly did this by testing a bunch of papers and then seeing what worked and keeping that and getting rid of what didn't. So if you're curious, it's summarized in that table. But over there, we have the chromatogram that I got using the EPA 521 nitrosamine mix, which is just a standard mix of 7 nitrosamines. Overall, the chromatogram looks pretty good. You want those sharp peaks. However, there are some issues that we would need to resolve in the future. So there's an overlap of baselines between 1-nitrosopyrrolidine and 1-nitrosodipropylamine. And also we have these broadening peaks at the beginning. So we can resolve that by trying a column with a more polar column chemistry. Because nitrosamines are polar compounds, using a more polar stationary phase can help separate these better and retain them to the column longer. And then for these initial peaks at the beginning that have broadening, we can also try a lower starting temperature just to keep them in the column longer. We also did a calibration curve in order to determine the limits of detection and quantification. And we got pretty low limits, but some of them are negative, which isn't possible since you can't have a negative concentration. But we would need to repeat in the future with lower standards just to kind of get closer to that true limit of detection and quantification. But we can expect to have limits in the parts per billion range since that's pretty standard for GCMS. And then we also determined the signal-to-noise ratio for each peak, and those range from 65 to 8,000. The signal-to-noise ratio just tells you how much a signal stands out from a background of noise. The lower numbers correspond to those earlier peaks that are pretty short, so most likely with the improvements that I mentioned, we could improve that. So moving on to the nitrisation reaction, like I said, we use piperazine, which is this amine up here. It has 2 different amine groups, and we formed 1-nitrosopiperazine, which is down here, so you can see that nitroso group. This was previously reported in literature, and we just kind of followed the procedures put in that state that this reaction could be catalyzed by carbon dioxide, meaning that carbon dioxide helps the reaction happen. So to carry out this reaction, we loaded a piperazine solution with carbon dioxide and then transferred that as well as sodium nitrite to a stainless steel reactor, and then we sealed it, heated it over the weekend, and then analyzed via LCMS-MS analysis. So for the LCMS analysis, we targeted the molar mass of piperazine plus 1 because we're operating in the positive ionization mode. We're just adding a proton to piperazine, or nitrosopiperazine, and so we were able to identify a peak corresponding to that, referred to as the parent ion peak. So that was good. And we also did not detect any 1,4-dinitrosopiperazine. So because piperazine has these 2 amine groups, you could, in theory, add 2 nitroso groups, but we didn't detect that, which was consistent with the paper that we based this experiment off of. So moving on to future directions, we still have a lot of work to do optimizing the GCMS and LCMS methods. Like I said, for GCMS, we should try out a new column and a lower oven temperature at the beginning, just to, again, better separate those peaks. For LCMS, we can vary the ionization parameters in order to increase the abundance of the parent ion peak. This is important because sometimes it may fully ionize that nitrosamine, and then we won't be able to tell if it's actually there or not. So it's good to have as much of that parent ion peak as possible. We also want to perform solvent degradation reactions on a lab scale so that we can get samples that better mimic what we would see in the field. This can help validate our methods for more realistic samples. And then finally, we need to develop methods for using field equipment since those had not arrived at the time of my project. So yeah, that's everything. Thank you, and I'll take any questions.
Hey, Sophie, what do you think a mobile emissions lab would look like? What would something, this would be something that'd have to be set up over and measure stuff for years, right? So what would that thing look like?
So it's going to be a trailer, and it's going to have, I'll go back, a few different pieces of instrumentation on it. Okay, so yeah, basically it would just be carted down to wherever the point source capture site is, and then we would use some of the instrumentation, and just do it there. It is more like months-long testing, ideally. So things like the PTRMS and the FTIR are very rapid, and we would be able to do it right away. But most likely we would just kind of do repeated testing over periods of time, and just set up for like a few months at a time, and then, yeah, that would just kind of be it. So it's not years long, it would be pretty quick.
Would these be discrete measurements? Would you be taking them individually, or would it be generally be continuous measurements?
So it depends on the instrument. For PTR and FTIR, we can do it directly. So just direct emit of the, as the gas comes off the top of the column, it can go directly in the instrument. However, for the GCMS and LCQ-TOF, we would be collecting it over time. We have like equipment that can condense the gas. So that would just be done over, the testing period, which would be set depending on, I guess, on how much we collect from that condensed gas, and then that would be analyzed. And that's mainly for the trace products, since we need to have like a higher concentration of those.
I'm surprised that the EPA or the state regulators don't have some requirement for measuring this stuff now.
Yeah, it's still in development. They've been detected in a lot of like food products and like food, drink, things like that, and like wastewater. So there is weight regulations, I think, for wastewater, and the EPA does have like methods for testing it. But since point source capture is relatively new, there's not really regulations yet.
Thanks, Sophie. Thank you.
And our next speaker is Mahati Somala.
Good morning, everyone. My name is Mahati Somala, and this summer I was at the NETL Pittsburgh site under the mentorship of Dr. Sandeep Bukka and Dr. Rishu Wright, and today I'll be presenting on physics informed machine learning for efficient pipe leakage modeling. So a little bit about myself. I'm a rising junior at Carnegie Mellon University studying mechanical engineering with a minor in machine learning. Prior to Mickey Leland, I worked in the Giant Lab developing ML for autonomous cloud point detection, and after undergrad I plan to earn my master's in mechanical engineering and pursue a career in energy technology. Starting off with some background, pipes are one of the most efficient ways of transporting fluids like methane and hydrogen across long distances. However, leakages and defects can cause irreparable damage to the environment. Therefore, it's important that we can detect these leakages early on. We can do this by running fiber optic sensors along the length of the pipe, which can detect fluctuations in stress due to pressure changes in flow. We can use an ML model to detect where the leakage is based on the type of signal. However, we'll need a large data set to train this kind of model, and in order to produce this data set, we'll need to run lots of costly simulations and experiments that may not be feasible. So how do we solve this problem? In the past, guided wave propagation has been used to detect leakages and defects along a pipe. A machine learning model was trained with Phoenix and Firedrake software and was able to successfully detect these defects. However, this still relied heavily on experimental data and costly simulations. Now, we can define our problem into a few key points. First, we want to develop a novel solution to incorporate experimental data and simulation data when solving fluid flow problems. We also want to address the challenges of computational fluid dynamics and model fluid flow in a pipe with leakages. So we propose a physics-based machine learning model as a solution to this problem. Rather than relying on extensive data sets, physics-informed neural networks, or PINs, rely on physics equations and principles to produce accurate data. So instead of using data to train the model, it's instead used to validate it. So how do PINs work? PINs are non-data-driven, meshless supervised models that satisfy an initial condition, boundary condition, and governing partial differential equation. The governing PDEs can be embedded into loss functions, and by minimizing these, the weights are constrained to these principles. This means that simulating pipe flow is much less costly and much more feasible. So this can be broken down into a few key points. But first, First, the question we need to answer is why use PINs over traditional CFD? So CFD, or computational fluid dynamics, relies on the finite volume method. This means creating large meshes over objects and iteratively solving partial differential equations to solve fluid flow. This can be computationally expensive and time-consuming, especially as models get more complex. On the other hand, PINs are physics-driven, so they don't require large amounts of memory to store meshes. Additionally, pins can include experimental data in their training, whereas this is not possible for CFD. And while pins may take a long time and may be difficult to train initially, once they've been trained, they can take in any inputs on the parameters they've been trained on. And while pins are not meant to replace CFD, which can be taken more as like a ground truth, they can be extremely useful when generating hundreds of thousands of test cases. The challenge with pins lies in tuning the hyperparameters and optimizing the geometry so that it accurately reflects the physical phenomenon. So my project for the summer focuses on developing a fluid flow model for pressure data. So one of the first steps I took was to see how leakages can affect pressure and velocity in pipe flow. So I modeled an 18mm diameter pipe with a 2mm circular leakage in ANSYS Fluent. And some assumptions I made were that the flow is steady state, which means there's no time component, and incompressible, which means the density is constant. So these are the velocity and pressure plots from my simulations. As you can see, I modeled leakages at 1.5 meters from the inlet, 0.5 meters, and then at both locations. And you can see significant fluctuations in velocity and pressure, which implies that we can detect leakages by monitoring things like pressure. So at this point, I could begin building a pin, and the software I used is called NVIDIA Modulus, which is an open source package of modules that allow for a structured way of solving pins. Here's the basic anatomy of a modulus project, where you can add validators, inferencers, and monitors to a domain upon which the neural network is solved. You can also create custom partial differential equations to use as loss functions. So these are some of the partial differential equations I used. They include the continuity equation and the Navier-Stokes equation, which account for conservation of mass and momentum. This is important when describing fluid flow and is useful when solving for velocity and pressure in pipes. Additionally, I use the following equations. In CFD, when simulating turbulent channel flow, which is characterized by more irregular flow patterns, the meshes near the boundaries can become overly complicated and difficult to solve. So we use these wall functions to help out with this computation. Specifically, I use the K epsilon model, which solves for the turbulent kinetic energy and the dissipation rate. So the first model I built was a 2D turbulent channel flow, and the goal of this was to replicate the original CFD results and see how well the 2D channel geometry could describe pipe flow. And you can see here that the pressure profiles match well with the predicted results, especially with this parabolic velocity profile. And these are the plots from my model. So the pressure distribution here shows a constant pressure gradient, which also corroborates that the model was able to successfully model pipe flow. These two graphs compared the modulus results in green to the predicted results, which come from some open foam simulation data. And you can see that it's fairly matched to the points that we're focusing on. So next I applied a leakage to this geometry by adding a secondary 2D channel through the center of the pipe. And this was trained for the same amount of time as the original model. However, you can see that there's a few discrepancies in the pressure profiles, pressure and velocity profiles, although the general profile matches as there's parabolic velocity and an increased velocity in the y direction inside of the leakage. So this is a side-by-side comparison of the pressure distributions from each of my models. As you can see, there's a significant pressure fluctuation near the leakage point in the second model, which implies that it was able to successfully model how leakages affect pressure in pipe flow. However, the fit is not as clean as the original data, so this may imply it requires further training or hyperparameter tuning. So in conclusion, the result was that I was able to build a preliminary physics-based machine learning model to simulate basic 2D flow with a singular leakage. This is an important first step when we're trying to lighten the load of computational fluid dynamics and other costly experimentation and ways to collect data when we're training other machine learning models. However, we can further improve the current model accuracy, especially with further training, or one way that we can do this is by collecting validation data either through CFD simulations or some experimentation. This can help guide our hyperparameter tuning and make for a more accurate model. We can also use the tessellation geometry module in Modulus, which will allow us to import CAD files for a more holistic view of like 3D modeling, which is important when we're experimenting with 3D simulations, although we will also have to collect some validation data for that so that we can accurately tune the hyperparameters. I'd like to thank my mentor Sandeep and the entire MLEF staff for making this project possible. Thank you, and any questions?
Why is the fiber optic model so difficult to train? Let's call the fiber optic model the dog, and the physics model like, the person,
Yeah.
right? So why is it so difficult to get the dog trained up front?
Yeah, so generally when we are collecting data for that kind of model, we might need to say we were running an experiment where we had a pipe with a leakage. We can't feasibly start leaking methane into the environment and just keep collecting data like that. On the other hand, if we were to do CFD simulations, some of those take hours and hours to run. For example, the 3 simulations I ran took 1.5 hours to build and solve. So that kind of adds up when you're building a large database. So physics-informed machine learning doesn't really rely on that kind of data, and it can kind of replace that load of trying to collect so much data that's difficult to collect.
And once you get the dog trained properly, is there a feedback loop that makes the physics model, the physics-based machine learning model better? Is there a sort of an iterative process that everybody gets smarter over time?
Yeah, so I think as you're collecting data, that can also be used to validate. Generally, the physics-informed model is extremely primitive right now. So I think as we get more information and we can better understand how to reflect the physical phenomenon, it could definitely be a loop of information and hopefully make one that's extremely accurate.
Thanks.
And our next presenter is Nathan Gull.
All right. Hello, my name is Nathan Gull, and today I'll be presenting on the effective support on iron-based catalysts towards carbon dioxide-free hydrogen production from methane pyrolysis. My mentor for this project was Devaka Reddy at NETL Morgantown. This is just a disclaimer. So a little bit about me. I'm from Frederick, Maryland. That's about an hour away from where I go to university at the University of Maryland, Baltimore County. There I'm a rising senior undergraduate in chemical engineering. I have prior research experience there working with dilute organics and cloud water samples and determining secondary reactions in the atmosphere there. And a fun fact is I love to sail. I've sailed against people from around the world. So carbon dioxide, as we all know, is a major focal point of today's society. One such source is steam reforming of methane. This process takes 1 mole of methane and produces 1 mole of carbon dioxide and 2 moles of hydrogen. This sounds like a good ratio, but in reality, that's not. That's 5.5 kilograms of carbon dioxide to 1 kilogram of hydrogen. So today's industry is dominated by this reaction, but it's not the only reaction. We also have water electrolysis, but this takes a lot of energy. It's 285 kilojoules per mole, and while it is emissions-free, if that energy is not emissions-free, that energy comes from a coal plant, then technically this process is also dirty. That's where methane pyrolysis comes in. It's a lot more energy efficient than steam reforming of methane and water electrolysis. It is emissions free. This takes 1 mole of methane and produces 1 mole of pure elemental carbon and 2 moles of hydrogen. So why aren't we using this already? Well, it's all based on cost. So steam reforming methane is $1 per kilogram of hydrogen. Water electrolysis, 5.5. If you look at methane pyrolysis, it's $1.30. This is kind of our issue. So looking at literature, different people have tried to use catalysts to lower this, or to increase the efficiency and lower the cost. So doing a whole literature review, we saw that they used a couple different catalysts, namely iron and nickel. So nickel is all the way down at temperature activation of 600 degrees, which looks really good, but nickel deactivates very quickly. And it's really expensive. If you look at iron, it's all the way at 800, which is a little bit higher, but iron's very cheap. So we went and looked at literature to determine different catalysts in literature based on iron. As you can see, they're kind of all over the place. We have a lot of different flow rates for this, all the way up to 42 liters per gram hour, and then all the way down to like 4.5. This is not ideal, as we can't really compare these results. And if you look at the methane conversion all the way on the right, you'll see we have a 92% conversion compared to a 38%. This is just not ideal. So our goal is to try and take 3 different supports and optimize them underneath iron to try and figure out like how the support interaction actually affects this reaction. So in today's presentation, I'll be going over the synthesis, so how we actually created our catalysts. Then I'll be going over our actual reaction conditions, so how we determined that we could say the support is the actual change in our product rather than say a flow rate or a temperature change. In the second half, we'll be going over the characterization, so what processes we actually did to determine the products and their actual quality. And then we'll be tying it all together, trying to determine a mechanism based on these supports. So I want to reiterate, what we're trying to do is we're trying to determine the effect between the support and the metal catalyst and try and increase the hydrogen yield and choose the highest one. So starting with our synthesis, we use a technique called wet impregnation. This is a very cost-effective technique. You take 2 pieces, namely our iron and our support, and you mix them in a water ethanol solution. We did this in a 60% by weight iron to a 40% by weight support. So the only difference we're going to be seeing in reaction when we change these supports is the actual support difference between the 3. As you can see on the right here, we have 3 different catalysts. We have our iron on ceria, iron on alumina, and iron on silica. We then did a BET analysis once we once we made our catalysts. This gave us our surface areas, which we concluded that it wouldn't affect reaction based on the surface area change. So looking at the actual reaction, we did first 5 different reactions. We chose iron on alumina, as this has been the most studied in literature. And so if you look, we have 2 liters per gram hour. It increases the whole time. This is not ideal. We want steady state reactions so that we know the only thing changing is the support. So that's why we chose 6 liters per gram hour. As you can see, we did 6, 12, 24, and 48, but 6 liters per gram hour gave us a stable yield at 40%. So we then did 3 more reactions. We swapped just the catalyst. So we have iron on alumina, iron on silica, and iron on ceria. And as you can see again, iron on alumina performed the best and was stable. The iron on silica and iron on ceria both decreased throughout reaction, and this is due to their support metal interactions, as we'll see later. So how can we characterize our products? Well, first we actually have to look at the reactants. So before we did before we did the reaction, we did XRD on our actual catalysts. So here you can see iron on silica and iron on alumina have very similar profiles. These profiles match this line at the very bottom. This is hematite. So hematite, the dominant peaks here match directly up here. As we can see with iron on ceria, it also has these peaks. However, it's got another set of peaks. This is FeCO2. This hints at a strong iron support interaction and is also supported by our spent catalyst graph over here. If you look at iron on ceria, we see a much larger FeCO2 peak that matches with this green down here. We also see an elemental iron peak here, but we've got a lot of noise around that, so that means we have iron carbide as well. That leads us to iron on silica, where we have iron carbide, but we also have this elemental iron peak. The iron carbide is due to a weak support metal interaction, so the iron is really just deactivating. If you see iron on alumina here, we have a much larger elemental iron peak. This peak is what we believe is the dominant site, but it's not our most important peak on our graph. If you see here, we have graphitic carbon. So we have 3 different peaks, and it's largest in iron on alumina. This tells us that we had the most product, which also just verifies what our reaction data told us. But how can we determine the quality of our product? That's where Raman spectroscopy comes in. Here you can see 3 different graphs, and then you see 2 peaks here that we're going to focus on, ID and IG. ID is our disordered carbon, or carbon that is short and not crystalline in nature, but it's still carbon nanotubes. IG, over here, is our larger, longer nanotubes that are crystalline in nature. So if you take ID by IG, you get this table over here where we have a ratio. The lower the ratio, the better the crystallinity. So after knowing that our iron on alumina had the most product, we're being told that iron on alumina has the worst and iron on ceria has the best. This doesn't really make sense, but it's kind of misleading. If you see here, we have a large peak in iron on alumina and a large peak for ID. This could be due to the fact that we have the most product in our iron on alumina. So it could really be that we have more graphitic carbon in iron on alumina that is of quality than even in the ceria because we had more product. So tying this all together, what this data tells us is that we have a couple different mechanisms. So the first being iron on alumina, where it's actually deposited on the support, and then the nanotubes grow underneath. And after they grow for a certain distance, the iron falls off and then forms with iron carbide and deactivates. The iron on ceria here actually is bound to the ceria. So when it's bound to the ceria, it can't move, and so we'll get some nanotubes, but then it will just deactivate and be covered in carbon. One not pictured here is iron on silica, and it's similar to this here, where we have very few bound to the support, and most of them are just kind of floating around. These iron nodules will react with methane, but only once, and then once they form that carbon, they'll actually deactivate. So all of this is just like presumptive. We want to do in situ analysis to determine this, so that would be XRD and Raman at temperature, so then we can determine whether the carbon is forming at different times, like if it's forming the disordered carbon first and then the nanotubes, and that'll just allow us to verify our mechanisms. So in conclusion, we know iron on alumina is our best option, and so we want to do these future works to determine or to increase the efficiency of this reaction, as it is very promising. I'd like to thank the entire reaction engineering team, especially my mentor, Devakar. And then I would also like to thank the NETL staff, the MLEF team as a whole, and every single one of the fellows who has been here this whole week. So thank you very much. Sweet. Any questions?
Could you go to the graph where you were showing why you chose like the particular, yes, this one. Sorry if you've already covered this. I was wondering, with the varied flow rates, were you also testing the different supports in that test as well? Or did you like pick one of those to test?
Could you repeat that? The difference in what?
So you have the varied flow rates, right?
Mm-hmm.
Did you test varied flow rates with just say one of the specific supports that you had?
Yes.
Okay.
So we did this on iron on alumina. It's been the most studied in literature, and it was our most promising catalyst. So we decided to go with that and then compare different interactions. So.
Okay, thank you.
While she's coming here, go to your methods of hydrogen production from the things like.
Gotcha.
Yeah, very good. Yeah. So if you had to put a percentage of hydrogen produced from those 3 methods today,
Okay.
what would the percentages be for each one of those circles?
I'd say, so in industry, I'd say this is probably 95% is steam reforming methane. It's mostly that. It's a very efficient process right now. It's very industrialized, so we don't need to put anything in place. And then water electrolysis, a lot of excess energy goes there, so it's not really like a primary sort of function. So, and then methane pyrolysis is very new. It's not industrialized yet, so it's still lab scale, maybe a little bit larger than that, but there are plans to kind of move that forward.
So recognizing that this methane pyrolysis approach is a blueprint that you're trying to provide industry, the difference between the cost of 99 cents and $1.30, that's not very much. So what's driving that additional 31 cents? What do you think the cost is, and how do you get that down to compete effectively with steam reforming?
Your catalyst costs. So typically they'll use nickel or cobalt, which heavy metals are toxic and expensive. So there's kind of that cost there. One thing I'd like to point out though is the efficiency. So methane pyrolysis is like 58% efficient in terms of energy, and steam reforming of methane is 60% with carbon capture. So the way that I kind of see this is methane pyrolysis can only become more efficient, and steam reforming isn't going to be that much more efficient. We've already kind of maximized it. So.
Great. Thanks, Nathan.
One more behind you.
Great presentation. I was wondering if you can go to slide 10.
Gotcha.
Basically, if I understood correctly, you said that the carbon crystalline quality was contradictory to the results you found in the previous slide, and that was because of the large amount of carbon that the iron-on alumina produced. I was wondering if you could have normalized the data by removing the amount of carbon, and that trend would flip.
Right. Yeah. So that was this was kind of at the end of like our whole summer, so we didn't have time to normalize it. But yes, you definitely could and get different results. I don't think it would change too much, just because the iron did form a lot more. So the ratio would, I mean, that would definitely verify what you're saying.
Thank you.
That's it. So for our last speaker today, we have Jennifer Garcia.
This one? Okay. 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 Hello everyone, my name is Jennifer Garcia, and I will be presenting my research on the feasibility of using power lines for geophysical subsurface imaging. A little bit about me: I am currently attending University of California, Riverside. I am an applied mathematics major with a concentration in physics. And after I complete the Mickey Leland Fellowship Program, I am going to be entering my senior year, which I hope to finish off strong. And then after eventually gaining work experience, I'd like to go back to school. And a little fun fact about me is that my guinea pig's name is Dewey Decimal. Okay, I know we've all heard this already, but a little bit of background. As we know, there has been a steady increase in greenhouse gases, with the exception of the sharp decline in 2020 due to COVID-19. Now we have surpassed the amount since then, and it's mainly due to the economy. The main sectors in the United States that contribute to the most greenhouse gas emissions and sinks are transportation, electricity production, and industry. The main culprit of these gases is carbon dioxide, which is mainly produced by fossil fuel combustion. There have been many efforts to reduce carbon emissions, but the most efficient one being carbon capture and storage. There was a lot of consideration into selecting a site for carbon dioxide storage. We need to consider the depth of the layer, how permeable and porous it is, and most definitely, there needs to be an overlying sealing system. To identify these locations, we conduct surveys and use model visualizations. This is when subsurface imaging makes its entrance. With subsurface imaging techniques such as seismic or electromagnetic, we're able to gather all the information needed to determine if a site is suitable for carbon storage. However, we also need to make sure that we keep an eye on carbon dioxide once it's injected underground. So this is when power lines come into play. One of the most extensive infrastructures in the United States is the power grid. Power lines show up as noise when using electromagnetic imaging methods, but we are wondering if there's a way we could use them to our advantage. Power lines have a standard frequency of 60 Hertz, which is already pretty low for deep layers,
So maybe we can use this to focus on subsurface imaging. Electromagnetic methods are sensitive to electrical conductivity in the subsurface materials. Meanwhile, power lines are already optimized for electrical conductivity, from their conductors having low resistance to their insulators preventing any electrical leakage. So, why are we so eager to investigate power lines as a possible source? There are over 180 million power poles in the United States alone, meaning that is over 5.5 million miles of power lines, each of which generate their own electromagnetic fields due to the alternating current flowing through each of them. This produced magnetic field extends outward in a circular pattern around the conductor, which then penetrates the Earth's surface and interacts with the subsurface materials. As the magnetic field penetrates the subsurface, it induces an eddy current in the conductive layers, which then generate their own secondary magnetic fields. Subsurface materials with different conductivities will interact differently with the magnetic field. So the more conductive they are, the stronger the eddy current will be. So how do we measure these secondary magnetic fields? We use receivers to measure the changes in the magnetic field's amplitude and phase over time and space. By analyzing the secondary magnetic field's characteristics, we are able to infer the subsurface's electrical properties. It is important we have a way to measure these changes in electrical properties because carbon storage sites can change conductivity. This can either happen through through the displacement of conductive fluids, mineral alteration, and even pore pressure changes. We think we can measure these conductivity changes because electromagnetic imaging methods are sensitive to the changes in the subsurface's conductivity. Unlike seismic methods, electromagnetic methods can directly measure electrical properties. By keeping track of these secondary magnetic fields over time, we can ensure that the carbon dioxide remains securely stored and does not leak into other formations or reach the surface. So, to test how feasible a power line could be for imaging through electromagnetic methods, we use a Python package called MPyMod to model and simulate electromagnetic responses under different subsurface conditions. We did analyze the amplitude, phase, absolute normalized plots, but I feel like difference plots are easier to read. In this example, we showed the post-CO2 conditions as just an increase in resistivity in the fourth layer. And as you can see, our frequency of 60 Hertz is found along the 1.78, and it remains red, showing a positive difference until it reaches the 0.1 kilometers mark, meaning that it cannot go further past it 100 meters deep to surface. To analyze geological formations, we did look into 3 different scenarios, one of them being the transition from brine to carbon dioxide in sandstone, and we did find minimal positive difference, meaning that it could potentially be used to detect the presence and migration of carbon dioxide. However, this difference in the plot is not very significant, so it's not strong enough. Our second scenario is a shale caprock. No changes were done in the resistivity layers to show how permeable the shale rock is. And as you can see, there's no changes, which is good, meaning that it effectively contains carbon dioxide. So a frequency of 60 Hertz would not be able to detect anything past then. Our last scenario is a carbonate reservoir. We did find positive differences, but they were not very significant, meaning that if we wanted to look more into this, we would need a more detailed modeling. We also decided to analyze any leakage detection scenarios. Our first example was a breach into an overlying aquifer. We did find minimal positive change. Still, it's not very significant to say that it can detect these. Our second example was a migration of carbon dioxide to shallow layers. We did find negative changes, but they were really, really subtle, if not the most subtle of them all. So it would not be very efficient in this type of scenario. Our last scenario was a breach through the fault zone. And this one did show the most significant positive difference, meaning that it could aid in potentially identifying any leakages from fault zones, but it would still need stronger, it would need better modeling and maybe additional equipment. So, is this worth further exploring? Based on these results, no. I would say that since it showed the most significant change in the fault zones scenario, I could think that if we were to pursue that, it would potentially show, it could work as a early mechanism for leakage detection. There are both advantages and disadvantages to using a power line, meaning that there's already like power lines. They're not gonna go away in the next few years, you know? So we could use those as a extra source in other imaging methods, such as ERT. And then, sorry. This is limited to the depth of penetration of 100 meters, so it can't go any further past than that. So it's just, it's only for just subsurface imaging. And yeah. Oops, sorry. Questions? Going once? Going twice?
Jennifer, we've been waiting for you for 4 days. For 4 days, you know. It's tough being the very last person, but I thought you did a great job. I think this subsurface imaging using power lines is a fantastic idea. You know, I've never really heard anyone talk about this, but when you say there are depth limitations, I mean, what do you think, you know, in feet or meters? I mean, how deep can you use the technique effectively?
I would say just mainly for analyzing what kind of formations are in the subsurface.
Yeah.
Because injections usually are 800 meters or deeper. So it can't really be used for monitoring the carbon dioxide that deep.
And do you think that this technique could be limited only to CO2, or could you monitor hydrogen or natural gas or other types of fluids?
My focus was mainly on carbon dioxide injections.
Yeah.
But I do think it could be used for other prospects.
Yeah. No, it's a really novel idea, and I think she did a great job, huh, folks? Yeah. Thank you.
So we'll take another break until 11:30, and then we'll have our last part of the technical forum program. But before that, let's give a huge round of applause to everyone who has presented today. And before we go on a break, I need to see two students, Shara and Natalia. If you could see me here, that would be great. Thank you.
Closing speaker, Dr. Marianne Walk, who is the new NETL director. She's joined us during this past year, coming over from the Idaho National Lab. I know we had at least one student here that was at Idaho. So we look forward to hopefully having more at that laboratory site in the future. Dr. Walk, can you hear me?
I can. Can you hear?
Yes, we can hear you as well. So welcome. I'll turn the floor over to you, and thanks for joining us today.
Well, thanks so much. And I've been able to hear the background for the last couple of minutes, and it sounds like you all are having a great time there. And I'm sorry I can't join you again. This will be the third time I've talked with Mickey Leland people, but never in person yet. So next year I need to do better. I've been at INL, see, there you go. I've been at NETL since February. I was at INL prior to that. And unfortunately, I was traveling last week and I came down with COVID after I got back to Pittsburgh, which is why I can't be with you today. I'm sure you don't want to get COVID, so unfortunately, I'm not going to be able to give you your certificates in person. Alan will take care of that. And I'm sure he'll do a great job. So, I wanted to be conservative around reactions, so I have to be remote. Anyway, I want to sincerely thank the mentors, the research advisors, the site advisors, and all the employees program folks to make this experience possible. Everybody worked really hard. A lot of dedication and time to this effort, and that makes a big difference. And congratulations, of course, and thank you to all the students who completed this year's Mickey Leland program across our national laboratories at NETL in particular, of course, and at headquarters. So I'm sure that your hands-on experience you've gained from the program will really prove to be valuable as you're moving through your career. This summer, you've all played a vital role in helping to address, as you know, the world's most complex energy challenges in support of DOE's mission of limiting environmental and climate impacts of fossil fuels and industrial processes while working to achieve net zero emissions. And I'm glad that you participants were able to present all your research findings at this year's technical forums. I'm very sorry I wasn't able to attend any of it, but I'm sure it was fascinating and demonstrated some excellent science. So recapping a little bit about NETL, for those of you who didn't spend your summer there, I know that many of you did, but our mission is to discover, integrate, and mature technology solutions that enhance our nation's energy foundation and protect our environment. So in addition, of course, to our cutting-edge R&D that we do every day, we also play a crucial role in creating and managing funding vehicles to support energy initiatives as a field office for the fossil energy and carbon management part of communities. That's also a very important part of what we do at NETL. And your work here in the program impacts the world in amazing ways. We truly believe that DOE is a solutions-focused agency engaged in a really wide range of challenging and innovative work, ranging from basic research to apply to some deployment and also national security. So now that you've completed this competitive program, you're joining the ranks of more than 1,000 of the best and brightest students from across the country that have made up the Mickey Leland program in the past and present. And so you're now part of our great pipeline of future STEM professionals. And each of you played a vital role in accelerating energy innovation during the course of this program. And I want to take a moment to touch on just a few of the research projects that were conducted at our labs this summer, pushing the boundaries of possible in energy technology. And I won't go into any detail, you've all seen all your presentations, but just in summary, we had 12 students working on projects related to advanced computational science and engineering. These were 12 at NETL, are crucial for evolving our simulation tools and our analytical capabilities. We had 5 students at NETL focused on materials engineering projects for energy applications. These are pivotal for enhancing our capabilities to develop materials that perform under extreme conditions. This is important for a lot of parts of energy and pushing forward the boundaries of current materials technologies. We had many students, 16, I believe, focused on projects enhancing energy conversion processes, things like understanding concepts like diversion and high pressure carbon dioxide pipelines, and extracting rare earth elements using multi-salt technology, for example. In an area near and dear to my heart, geological and environmental systems research, we also had more than 10 projects vital to managing environmental impacts of energy production and helping us enhance sustainable energy practices. I was excited to personally see projects related to things like imaging rock cores done at our METL Morgantown facility, several projects related to underground hydrogen storage, acoustic propagation, well, seismic imaging, and several projects related to rare earth elements and critical minerals. Finally, several students focused on projects that enhance systems analysis and engineering. It's really crucial for our decision-making processes, and this is really important. Sometimes I don't know. Ensuring that our research and development projects are both leading edge and also economically and socially sustainable. So please support the full breadth of what we do at NEPL and what FECM does and its core competencies in our shared goal toward our clean energy future. That you'll help to shape. So let's talk for a second of just about the future. This, I think, was hopefully for you much more than just a summer internship. I want to personally thank you for sharing your talents with us, for bringing your ideas, your energy, your creativity, and joining us in the important research that you did. Now that you've concluded your final presentations at the forum, certainly I encourage you to proudly carry your achievements into your future endeavors. If you're excited about driving change, tackling complex challenges, and contributing to a sustainable future, we also encourage you to continue to think about exploring job opportunities for your education at DOE, at NEPL, and within the National Lab Complex, at our National Laboratory. We have additional programs at our lab for undergraduate students, graduate students, postdocs, postmaster students, or finish their master's degree as well. And I would encourage you to explore that. You can apply through these positions through Intellect, or you can go to the USA Jobs website and select the student filter or the region graduate filter. I've been on the USA Jobs website. It can be a little bit intimidating, but I'm sure there are people who can help find the right job for that thing. So we at the Department of Energy like to provide many opportunities to positive difference in the community, and so please help us take advantage of this. Please take advantage of it. So in closing, we clearly need more STEM professionals in the movement. We also need diverse voices and perspectives because it's going to be integral to the future of STEM fields. With your contributions, we can succeed in making meeting our nation's evolving energy needs. So you are the nation's next generation of STEM professionals. And I hope that you continue to advance our nation's competitiveness by strengthening our capacity for scientific and technological innovation. And you will help us define the future of energy and the future of our planet. So thank you for engaging in this great experience this summer. I hope you found it to be enlightening, valuable, and fun. And once again, I encourage you to continue a fulfilling career in STEM fields, and hopefully within the DOE complex, such as at NEPL and the other DOE national network. So thank you very much, and I hope you have a very enjoyable certificate ceremony and a great rest of the summer. Thank you.
Thank you very much, Dr. Walk. Hopefully we'll see you in person at the next program.
I hope so.
Next we're going to ask Leah to come up and provide a few closing instructions and remarks from ORISE. you're going to want to pay attention to this, because I have a feeling she's going to talk about your last stipend.
Stipend,
Yeah.
reimbursement, when it
Right.
comes to money, let's pay attention. We like to talk about that part, right? Y'all have done a great job this week. I am always so impressed in what happens between the kickoff and getting here to the forum. I hope you've had fun. It is clear that you've gotten experience this summer. And so what happens next, I think we're all ready to support you, help you, guide you, answer questions, and celebrate. You made this, so great job. Couple of things. A few of you probably got an email this week that your kickoff expense reimbursements are still held up because you need to complete some actions on that. So if you got that email, please check that, log in to Concur from your Zintellect accounts. If you need help with that, you can reach out to our Travel Central team. We want to make sure and get those wrapped up because now that it's August, our end of our fiscal year happens in September. So we don't have a very long run time here to get everything wrapped up because we're immediately going to start on your expense reports for this trip. So I'm going to send you an email tomorrow with the job aid again, some other tips and tricks to help work through that. You'll expect to get reimbursed 10 to 14 days after those get completed. Your final stipends will be processed tomorrow, so you'll be receiving those. Your expense reimbursements will come separately, but to your same account. Last thing I'd want to remind you about too is you will also be getting a link to a final survey about the program. That will probably come tomorrow too, could be Monday. And we'll ask your, be honest. We really pay attention to those answers. Christina and Sandra and team really are thoughtful and think about how to make the program better every year. And so your opinions and thoughts matter. So here's your chance. We'll ask for you to have that completed no later than the end of August, but the sooner the better. It's been a great honor just getting to see all the things that you've done, get to know you. Again, if we can help you in any way, let us know. But we want to get you paid, so let's help get those expense reports done on time. So congratulations.
All right, thanks, Leah, and thank you to you and your team at ORISE. We have a wonderful partnership with ORISE to make this program run efficiently and everything, and they are instrumental in helping us be successful, and most importantly, getting your arrangements made and getting you all your stipends and travel and all those things. And please do complete that feedback survey honestly, openly and honestly. It's anonymous, so we don't know who's saying what, but we do look at everything, and we do try to make this program as productive for you and as meaningful for you as we possibly can. So I hope it was that way, and we want to keep that up for the next 1,000 students that we'll encounter over the years, right? In the vein of thanking people, I want to take a moment also before we head into giving you all your certificates and the formal closing of our program. I want to thank several people. We have an outstanding team here at FECM and DOE who work tirelessly to put on this program, and so I don't want to, I've written some notes because I don't want to forget anyone because we do have such a great team. But I want to echo Dr. Walk and others who have thanked our mentors and our research advisors, hopefully if anyone's watching, and those who stopped by this week. We can't have the program without good mentors and research advisors, right? Also want to thank our site advisors across the DOE complexes where you were located. They work to get projects for you all to participate in and help coordinate and make sure you have a good experience at their sites. I want to, a special call out to Angela and Alicia over at NETL. Obviously, a majority of you are at NETL, and we have a wonderful partnership with NETL at headquarters to put on this program. I also want to thank Nicole and Brian for their efforts to take photographs of the sessions and get photographs of each of you up here at the podium doing your presentation and doing the live stream. So thank you very much. It's good to be. We haven't seen Nicole in 5 years, so but she was here doing this before for us. So it's good to see her again. Our speakers, alumni, and colleagues who came and presented or were on the panel this week, thanks to them. Of course, Reggie, thank you for being here, and Captain Hunter for attending virtually. I mean, it's wonderful, obviously, to have you here. I know all the students appreciate your questions, but also, of course, your interactions. I know Reggie would love to stay in touch with you and hear what you're doing as well. So, stay in touch with Reggie for sure. Who else did I have? I think I want to recognize Gina, who's NETL's Chief Diversity Officer. I think Gina is or was here. But we've got a great working partnership with her on recruitment. Dr. Walk mentioned, I think, a little bit about applying for jobs. NETL is really building out their entry level and student programs. So as you continue your education, we hope you'll be involved in opportunities there, as well as early career opportunities when you finish your school. And turning to headquarters, our wonderful headquarters team, Lauren and Sam, thank you for all your work. Do an excellent job. And Caleb for his efforts out in recruiting. And Sandra, who couldn't be here this week because she's in training, but who has been running the program for the last several years and kind of turning the reins over to our superstar Christina, who has really taken over and led it this year. So a big round of applause for everyone who I mentioned. Thank you for all your work. Okay, so what we're going to do next is we're going to hand out your certificates. So the way it's going to work is Christina is going to call your name, and you'll come up to the stage. Reggie's going to come up. We'll take a couple of photographs with you and your certificate, and then you'll proceed off stage, and we'll go through and get everybody up here and get your certificate. So I want to be the first to congratulate you, or maybe I'm not the first, but I want to also congratulate you on the great work that you did this summer, and wish you all the best. And please do stay in touch with your mentors and us here in FECM. All right, so with that, Christina, come on up.
So when you get your certificate, please come up the stairs and please go down the same way. I don't want to see anyone jumping on this end, please. So first up, one quick thing before we start the certificate ceremony. You're going to get a certificate today. You're actually going to get a second certificate via mail. We had a little bit of issue with the printing, so you're getting something today, but I will reach out to you later so you can provide me your updated mailing address. You might see what I'm talking about. Also, there's a little something for all of you behind your certificate, so don't miss on that. First up, Ethan Antonia. Madge Awarki. Hayden Joseph Bakes.
Sophie Basidola. Kendra Beersley. Kylie Brinsa. Naden Brown. Kiara Brucey. Santo Carvo. Lee Carlson. Adrian Cedilla. Ashwin Damodaran. Naden Denon. Samia Derrick. John Din. Gabriela Diorto. Gabriela is not in person today, but she is joining us virtually, so we'll make sure to get her certificate. Max Edelstein. Matthew Garcia. Jennifer Garcia. Anne Marie Gardner. Cassandra Garza. Urban G. Christopher G. Nathan Gold. Ashu Gupta. Rumesa Gurler. Helene Henstridge. Sally Hong. Dylan Hodge. Dash Kamriani Beer. Natalie Larios Chavez. Sadie Levin. Tessie Mohammed. Sophia Morgan. Emmanuel Murphy. Cashin Nelson. Jamie Notarangelo. Samuel O'Connor. Jennifer Overcliff. Lainey Roper. Cindy Rubio Carrillo. Mia Schilbach. Mahati Somula. Olivia Sward. Ana Carolina Torres Rivera. Natalia Velisa Bege. Thomas Bernardi. Alexis Westwood. And Julius Joe. So congratulations, 2024 Emily as follows. So before we conclude this year's technical forum, I just wanted to say a few words to you. First, this has been an incredible journey. It's been 10 weeks, but I actually remember meeting most of you when I schedule a meeting to let you know that you have been selected into this program. And I saw so much hope and so much potential, and it has just grown over this summer. we've seen firsthand the challenges that we currently have. I mean, the climate crisis is no joke. And today, I can sleep a little bit better knowing that the future is in good hands. You guys amaze me and surprise me this year with your projects. And I know that the responsibility that you have, sometimes it may not feel fair. It's something that you inherited from previous generations, but I am sure you're up for the challenge. So I am so grateful to all of you for putting this little grain of sand in your projects, and I truly hope that you will continue forward in careers in energy, even the Department of Energy or the Office of Fossil Energy. So programs like the Mickey Leland Energy Fellowship Program are designed to equip you with skills so you can help us tackle these challenges, so you can do better, not only for you, but for your families, your communities, and the generations that will follow. I encourage you to stay in touch with each other. You have built a network over the summer, so make sure that you nurture it. And not only keep up with each other, but also with your mentors, your research advisors, even your site advisors. They could be the person that will help you in the next step in your career, whether it is now or maybe in the next 5 or 10 years. As you move forward, I also ask you that you share the word about this opportunity, because we want to bring more students like you so we can keep providing the experience and the skills to help us tackle these challenges. Your boys might inspire the next class of MLEF Fellows. Well, thank you so much for your hard work, your dedication, and your passion. I saw it this summer, and again, I am truly impressed. I am so excited to see where you'll go. I do encourage to stay in touch with us. You have here someone that, whether it is in the next month, in the next year, or 5 years from now, if you ever have any questions, if you ever need advice, we're here. Just because you have concluded this program doesn't mean that you cannot reach us back. We actually want you to do it. Keep us updated in your future careers. And again, if you need anything, just let me know. Congratulations. I don't want to say that this is a farewell. I certainly hope that it's a see you soon. So thank you, everyone. So my last 2 announcements for this year's technical forum. We will take a photo outside of the ballroom, a group photo. And also, if you have your name tag, we're actually going to try to recycle this, trying to do our part for helping the environment. Santos has designated himself as the official name tag person for this year's 2024 Technical Forum, so please hand your name tag to him. Oh, the paper you can throw away. We just need the plastic sleeve. The paper, you can throw it away, you can keep it. I don't know if you all have scrapbooks or memory books. I sure do. Still have things from my program 10 years ago, so you can do with it as you wish.